Welcome back to the deep dive. I want to start today with a feeling that I think every single person listening right now is intimately familiar with.
Oh boy.
I'm talking about that specific kind of paralysis you get when you have like 20 tabs open on your browser, 3 PDF reports on your desktop, a Slack channel is pinging you, and you freeze.
It's the modern condition.
Yeah.
Total information overload.
Exactly. It's that feeling where you technically have access to all the human knowledge you could ever need, right? It's right at your fingertips,
Yeah.
but you cannot find the one specific answer you need to actually do your job.
Yeah, that's the difference between information abundance and information utility. They're two very, very different things.
And the narrative we hear, especially in the tech world, is that AI is the silver bullet for this. I mean, we have these large language models now. We've got Gemini, GPT-4, Claude. They can read millions of words in seconds. They can ingest entire libraries.
That is absolutely the promise. The context windows are getting just massive. You can upload a whole book, an entire code base.
But here's the hook for today, and this is really the question that drives the research we're covering. Does dumping a library on someone's desk actually help them answer a specific, complex question?
Right.
If I asked you, who is the second cousin of the general who lost the battle mentioned on page 405 of that history book I just threw at you, does having the whole library help?
Or does it just make you want to scream?
Right.
And surprisingly, it turns out AI models suffer from the exact same paralysis. Just because they can read it all doesn't mean they know how to find the answer.
Yeah.
In fact, giving them too much information can actually make them, well, dumber.
That is a wild concept, and we are absolutely going to unpack that. The paper we're diving into today is titled Inference-Scaling for Long Context Retrieval Augmented Generation. It's by a team including researchers at Google DeepMind and the University of Illinois. Now, I know that title sounds like a mouthful of technical salad.
It does sound a little dense on the surface, for sure.
But the implications are just fascinating. And the mission for this deep dive is specific. We aren't just going to look at the results and say, wow, the numbers went up. We want to know the methodology.
The how.
Yes, the process. How did these researchers design a system to make these massive AI brains actually smarter, not just more stuffed with data?
Right. We're looking at how to give the model time to think and maybe a strategy to study rather than just hoping it absorbs everything by osmosis.
Before we get into the nuts and bolts, let's establish the core concept here. We're talking about RAG, Retrieval Augmented Generation. I always think of this as the open book test for AI.
That is the perfect analogy. Absolutely. In a closed book test, you rely on your memory, what you were trained on. In an open book test, or IterDRAG, you can look things up. You retrieve documents from Wikipedia, from a corporate database, whatever, and you use them to generate an answer.
Simple enough. But here is the twist, and this is what drove this entire paper. Standard IterDRAG, the way, everyone has been doing it for the last couple of years, it often breaks.
It does.
You'd think, hey, if the AI isn't getting the right answer, just give it more documents, give it 100, give it 1,000.
And that is exactly where it goes wrong. This paper points out that when you just add more documents, you introduce noise. The performance plateaus, or in some cases, it even drops. The AI just gets distracted by all the irrelevant text.
So the solution isn't just more data, it's better strategy. The authors propose 2 new methodologies, DRAG and IterDRAG.
Which I know they sound like drag racing terms, but they are actually these really sophisticated ways to scale inference computation.
We love a good analogy here. So if standard RAG is a student who's just, glancing at a textbook,
Then IterDRAG, that's demonstration-based RAG, is more like a student who studies previous exams to learn how to take the test.
okay.
And IterDRAG, well, that's becoming a detective who follows clues step by step to solve a mystery.
I love that. Okay, let's really unpack this. We have to start with the problem itself. Why is this so hard? I mean, we have these long context models now, like Gemini 1.5 Pro. They can handle 2 million tokens. That is an insane amount of text. Why can't they just figure it out?
Well, it's what you could call the context window paradox. You have this massive, massive window. You can fit a novel, a whole code base, a legal archive in there, but capacity does not equal attention.
Right. Just because I can fit a whole cheesecake in my fridge doesn't mean I can find the pickles in the back.
Precisely. The researchers highlight previous studies showing that once you retrieve more than, say, the top 10 documents, standard models start to struggle. It's that distraction factor. The correct answer is buried in this pile of irrelevant facts, and the model, just like a human, can lose the signal in the noise.
And this gets even worse when the question isn't simple, right? We aren't asking what is the capital of France. We're asking what the paper calls knowledge-intensive tasks or multi-hop queries.
Yes, the complexity gap. A multi-hop query is where you need to combine two or more separate pieces of information to get the answer.
The paper uses a great example. Who was the last emperor of the dynasty that succeeded the Song dynasty?
Okay, think about the mental gymnastics required there. First, you have to know, what dynasty succeeded the Song? That's the Yuan dynasty. Okay, hop one complete. Now hop two. Who was the last emperor of the Yuan dynasty?
Right, and if you just search that whole phrase in Google or, some internal database.
You're going to get a mess. You might get a Wikipedia page about the Song dynasty.
Right.
You might get a list of all emperors from all dynasties. You might get a random fact about the Ming dynasty. IterDRAG just grabs all these documents, throws them at the model, and says, good luck.
And the model just hallucinates?
Often. Or it just grabs a name from the wrong dynasty because it's mentioned nearby in the text.
So the goal of this methodology, the mission these researchers went on, was to figure out how to convert more compute into better answers. They wanted a linear relationship. If I give the model 10 times the amount of reading material or 10 times the amount of thinking time, I should get a predictably better result.
Exactly. They wanted to break through that ceiling where more data just equals more confusion. They wanted to create a system where the model learns how to process the external information, not just see it.
Okay, so let's get into the high-level approach. The paper talks about inference scaling. We should probably clarify what that means, because usually when we talk about scaling AI, we talk about training, make the model bigger, more GPUs.
That's a great point. Yeah, training scaling is about building a bigger brain. Inference scaling is about using the brain you have more effectively, but at test time.
So during the exam.
During the exam, it's about test time compute. They aren't retraining the model here at all. They're just changing how much work the model does while it is trying to answer your question.
And they have a specific metric for this work, right? Effective context length.
Yes. This is their currency. It's their unit of account. Effective context length is the total number of input tokens the model processes across all its attempts to answer a single question.
So if I ask the model to read one page, that's a low cost. If I ask it to read the page, then look at 5 examples, then write a draft, then read another page, that's a much higher effective context length.
Exactly. You are spending more tokens to, in theory, buy a better answer. And the methodology relies on 2 pillars to spend this budget wisely. The first is in-context learning, or ICL.
Which is basically showing, not just telling.
Correct. Instead of just giving instructions like, use the documents to answer the question, you give examples right there in the prompt. You say, here is how a smart agent solves this kind of problem.
And the second pillar is iterative prompting.
Which is the loop. It's allowing the model to stop, think, ask a follow-up question, and then go back to the library. It's moving from a single reflex answer to a genuine chain of reasoning.
The paper has this fascinating concept of allocating compute. I really like this because it feels very economic.
It is.
You have a limited amount of attention, or tokens. You can spend that on retrieving more documents, giving the model more raw knowledge. Or you can spend it on more examples, giving the model more instructions on how to use the knowledge.
And the entire paper is essentially trying to find the mathematical sweet spot. Is it better to have 100 documents and 0 examples, or maybe 50 documents and 20 examples? It turns out you have to balance them. It's not one or the other.
All right, let's dive deep into the first solution they came up with. DRAG. D-R-A-G. Demonstration-based RAG.
This is the big shift. This is moving from here is the data to here's the data, and by the way, here's what it looks like to use it correctly.
So in standard RAG, you retrieve some docs, you slap the question on the end, and you just hope for the best. What is DRAG doing differently?
It uses what they call a many-shot approach. They aren't just giving 1 or 2 examples. Depending on the context space available, they might include up to 28 examples, or even more.
28?
Yeah, and these aren't simple question and answer pairs.
Right, I was looking at the structure of these examples in the paper. It's massive. Each example in the prompt is a full simulation. It has a section for retrieve documents, then the question, and then the correct answer.
So it creates a pattern. The model reads example 1, and it sees, here's a bunch of messy retrieved documents, here's a question, and here's how the correct answer was precisely extracted from that mess.
Okay.
Then it sees example 2. Same thing. By the time it gets to your actual question at the very end, it has learned just in the context of that one prompt, how to ignore the noise and find the signal.
It's like watching a chef chop onions 20 times before you were asked to chop one yourself. You pick up the technique through observation.
That's it exactly. It utilizes in-context learning to teach the search capability itself.
Now, there is a specific step in the construction of DRAG that I found really detailed and honestly kind of surprising. It's about the order of the documents.
Ah, yes. The
Wow.
document reordering. This is a crucial blink-and-you-miss-it detail that has a huge impact.
So they use a retriever. Specifically, they mention Gecko 1B, which is a dense retriever, to find the documents from a huge corpus like Wikipedia. But they don't just paste them in order of relevance, 1, 2, 3, do they?
No, they do the opposite. Typically, a search engine gives you the most relevant result at position 1, then the next most relevant at position 2, and so on. But the authors explicitly mention reversing the order. They place the highest-ranked, most relevant documents closest to the query in the prompt.
Wait, so the best document is at the very bottom of the reading list?
Or next to the question.
Why? That feels so counterintuitive. If I'm reading a report, I want the headline first, the most important thing up front.
Humans? Maybe. But LLMs have a known bias, actually 2 of them. There's the lost-in-the-middle phenomenon and a recency bias.
Okay.
They pay significantly more attention to the text at the very beginning of a long prompt and the text at the very end, right before they have to generate their own text. The stuff in the middle can get lost.
So by putting the best evidence right next to the question at the very end.
You are practically shouting the answer at the model. You're putting the most important clue right in front of its face just as it's about to speak. It ensures the model focuses on the strongest evidence right before it generates.
It's a simple engineering trick, but I bet it makes a huge difference.
It really does. It's hacking the model's attention span.
That is so clever. So we have the retrieval, the reordering, the massive prompt with all these examples, and then what happens?
Then inference. The model takes this huge prompt, which might be hundreds of thousands of tokens long, and it generates the answer in a single pass.
And the logic here is that because it has seen 20 other examples of ignore the document about the Ming Dynasty, focus on the Yuan Dynasty, it now knows to do the same for your actual question.
Precisely. It turns the task from answering into pattern matching. It's not reasoning from first principles. It's mimicking the reasoning style of the examples it just saw.
There is a limit.
There is always a limit.
Even with DRAG, even with all these examples, the paper mentions that for really complex questions, it still struggles.
Right, DRAG is a single pass. It reads, it answers. But remember that Emperor of the Dynasty succeeding the Song question.
Yeah.
Well, if the initial retrieval step at the very beginning didn't happen to find the specific document about the Yuan Dynasty emperors, then no amount of examples will help. The information just isn't there in the context.
Because the initial search was for the dynasty succeeding the Song, it didn't know to search for Emperor Togon Timur or whoever the last emperor was yet.
Exactly. The retrieval step missed the second piece of the puzzle. You can't answer a question if you don't have the necessary documents.
Okay, so enter the second methodology, IterDRAG, the iterative demonstration-based RAG. This sounds like the heavy hitter.
This is where we add the dimension of time or steps. This is the part designed to break that compositionality gap.
The compositionality gap being the difficulty of combining disparate ideas.
Correct. It's hard to chain things together.
Okay, walk us through the life of a question in IterDRAG. I ask my complex emperor question. What happens first?
So step 1 is query decomposition. The model does not try to answer the question. It is prompted, again, using in-context examples, to generate a subquery.
A subquery, so it breaks the problem down.
Yes. For that emperor question, the model might output something like, follow up. What dynasty succeeded the Song dynasty?
It asks a foundational, simpler question first.
Right. And the paper uses a specific format for this called self-ask. It explicitly forces the model to generate the text follow-up question. It's a structured way of thinking.
Okay, so it has this sub-question. Does it just answer it from its own internal memory?
No, and this is the critical difference from things like chain of thought. This is step 2, interleaved retrieval. The system takes that specific subquery, what dynasty succeeded the Song, and it runs a brand new search just for that.
A dedicated search, just for that one part of the puzzle.
Exactly. It goes back to Wikipedia, finds documents that specifically talk about the Song-Yuan transition, and it adds those new documents to the context.
That is huge, because now the search terms are simple. Dynasty after Song. That's an easy Google search.
It's a dead simple search. Search engines love simple queries. They hate complex nested logic. So IterDRAG turns one hard search into several easy searches.
Okay, so it gets the new docs. Then what?
Step 3. Intermediate answer. The model looks at the new documents it just received and answers only the subquery. It might say, intermediate answer, the Yuan dynasty succeeded the Song dynasty.
Okay, so now we have a fact established, a building block. We know it's the Yuan.
Now, step 4. The loop. The model looks at the original question, it looks at its first finding, the Yuan dynasty, and it realizes, okay, I know the dynasty, now I need the emperor. So it generates a new subquery.
Like follow up, who was the last emperor of the Yuan dynasty?
Exactly. And it runs another search.
Another search.
Yes, specifically for Yuan emperors. It gets those documents. It generates another intermediate answer.
So it's building a chain of reasoning, but every single link in the chain is reinforced with fresh research.
That is the perfect way to visualize it. It's dynamic research. And this process repeats, they say, up to 5 times.
5 times? Why 5? Why not 20?
Well, efficiency is a big part of it. Each loop costs tokens and time, but also there's a real risk of error propagation. You get step 1 wrong, then step 2, 3, 4, and 5 will almost definitely be wrong. The chain breaks. So you don't want it to go on forever, chasing its own tail.
That makes sense. Okay, so finally, after the loops, we get to step 5, final synthesis.
Right. At the very end, the model now sees the original query. It sees the entire list of subqueries it asked. It sees the entire list of subqueries it asked. It sees all the intermediate answers it found, and it sees all the retrieved documents from every single step.
It's got the whole case file in front of it.
It does. And then it's prompted to say, okay, based on all of this, the final answer is X.
That feels so much more robust. It's actually showing its work.
And just like DRAG, they train the model to do this using in-context learning. They have to create IterDRAG examples.
How do they even make those? Because that sounds really hard to handwrite.
The paper mentions they filter existing data sets to find questions that naturally have these intermediate steps. And they use those as demonstrations. They show the model. Here is a question. Here is how a human broke it down. Here's the search they did. Here is the answer they found.
So the model isn't just learning to answer. It's learning the procedure of inquiry. It's learning how to be a researcher.
It is learning a workflow, a methodology.
This is a really good moment to pause and contrast this with what most people are using today, because I think a lot of listeners might be thinking, well, isn't this just what ChatGPT does when I ask it to think step by step?
That is the big confusion. And that's a different technique called chain of thought, or CO2.
Right.
Chain of thought asks the model to break down the problem, yes. But usually, CO2 relies on the model's own internal memory, or it relies on that first single retrieval dump we talked about with standard argy.
So Coty is like sitting in a room, closing your eyes, and thinking really hard about the problem.
Right. Or thinking really hard while looking at that one pile of papers you grabbed at the very start. IterDRAG is different because it actively leaves the room to go back to the library at every single step.
It validates its thinking with external data dynamically.
That's the key differentiator, the interleaved retrieval. It gets new information based on what it just learned a second ago.
That's a whole other level. And compared to, say, zero-shot QA.
Well, zero-shot is relying entirely on internal training memory. That's the closed book test. Drag and IterDRAG are fundamentally relying on external data, Wikipedia in this case, plus these guiding examples.
And compared to our baseline, standard DRAG.
Standard DRAG treats the model as a black box. It's input docs plus question output answer. It just assumes the model already knows how to read and synthesize. Drag assumes the model is a bit lazy. Or maybe just overwhelmed.
Yeah.
It assumes the model needs to be shown how to read the context effectively.
It's the difference between giving someone a tool and giving them a manual for the tool.
A manual with pictures and examples.
Even better. Okay, I want to move to what I think is the most scientific part of this deep dive, the inference-scaling laws.
This is where the scaling part of the title really comes into play.
The authors make a pretty bold assumption here. They assume that performance can be mathematically predicted based on how much compute, how many tokens you allocate to a problem.
That is the core assumption. They believe this isn't random magic, it's physics. Or at least it's predictable engineering.
And what did they discover? Did it work?
It worked shockingly well. They found a nearly linear relationship. When you plot the effective context length, so how much work the model did on a log scale against the performance accuracy, it's a straight line.
You're telling me it's a straight line going up.
A straight line going up and to the right.
That is incredibly satisfying to hear.
It is. From a scientific perspective, it's beautiful. It means if you increase the amount of text the model processes by an order of magnitude, say, from 10,000 tokens to 100,000 tokens, you get a predictable bump in accuracy.
If you use the optimal configuration.
That is the big if. That is the crucial caveat. You can't just spam tokens by adding 1,000,000 documents. You have to use the optimal mix of docs and examples that their method discovers.
This brings us to their computation allocation model. This sounds like something a CFO would love, a budget for thinking.
It is essentially a budgeting tool for AI inference. The authors developed a model, we'll skip the math formulas, don't worry, to predict the optimal configuration for any given token budget.
So if I say, I have a budget of 50,000 tokens to answer this question, the model tells me how to spend it.
Exactly. It answers the trade-off question we talked about earlier. For 50,000 tokens, should you use 100 documents and 0 examples? Or 50 documents and 20 examples? Or some other combination?
And what did they find? What is the general rule of thumb?
The finding is that you absolutely must balance them. Just adding more documents has diminishing returns. That's the plateau we talked about at the start. But adding examples, the shots, helps unlock the value of the documents.
That is a great way to put it. The examples unlock the documents.
I think of it like buying more ingredients for a kitchen. At a certain point, more raw ingredients don't help if you don't also have more recipes, which are the demonstrations. You need both to make a better meal.
And the paper assumes you can quantify the informativeness of a document and an example to predict this score ahead of time.
Yes, they essentially calculated a value for adding one more document versus adding one more example, and used that to plot these predictive curves. And the predictions from their model matched the real-world experiments almost perfectly.
That is wild. It suggests we can actually engineer intelligence, not just sort of hope for it to emerge.
It suggests that thinking harder, which is inference time, is a reliable substitute for being smarter, which is model size, or knowing more, which is training data.
I want to synthesize why each of these little steps matters, just to make sure we have it locked in. We talked about reordering docs.
And that's to fight recency bias. LLMs read the end of the prompt better, so you put the gold at the end. Simple as that.
We talked about demonstrations, the many-shot approach in DRAG.
That converts the task. It stops the model from guessing and starts it mimicking a good process. It aligns the model's behavior with the specific task of RAG reading.
And then we talked about iterative retrieval in IterDRAG.
That improves recall. A complex question is a terrible search query. Breaking it down into simple questions creates great search queries. Search engines handle simple queries perfectly. It effectively simplifies the world for the retriever.
And the limit on iterations, why stop at 5?
Error propagation. If you let it think for too long, it might overthink itself into a hallucination or get stuck in a loop. 5 steps seems to be the sweet spot for the current generation of models.
You know, as we're talking about this, I'm realizing something. This methodology, it really shifts how we think about smart AI completely.
How so?
Well, for the last few years, the whole race has been about training. GPT-3, then GPT-4, now Gemini, bigger, more parameters, trillions of parameters.
The bigger brain hypothesis. If we just build a big enough brain, it'll figure it out.
Right, but this paper is saying, hey, maybe the brain is big enough for now.
Maybe we just need better study habits.
Exactly. Better inference strategies. It proves that more context is only useful if you have a strategy to manage it. You can have the entire Library of Congress in your context window, but if you don't have a method like drag or IterDRAG, you're just lost in the stacks.
It democratizes performance in a way, too. This paper used Gemini 1.5 Flash. That's a smaller, faster, cheaper model compared to the big flagship ones. But by using IterDRAG, by letting it think and research iteratively, it outperforms standard RAG on much larger, more expensive models.
That is the aha moment for me right there. A smaller model, working smarter, beats a big model working dumber.
Precisely. It's the difference between a kind of lazy genius who answers off the cuff and a very smart, diligent student who does the research. The student wins on the complex questions every time.
So let's wrap this up with a provocative thought for our listeners. We usually end with something to chew on. If we can scale performance this linearly just by making the prompt longer and the process more iterative, if we can just buy more intelligence with a bigger token budget at inference time.
Where does it stop? What's the limit?
Exactly. Do we really even need much larger models, or could we achieve something that looks a lot like superintelligence simply by letting a smaller model think and research for days?
I mean, imagine an agent that when you ask a truly hard question like, How do we cure this specific type of cancer or solve this intractable physics proof? It doesn't answer you in 2 seconds. Imagine it runs an IterDRAG loop for a week,
Wow.
using millions, maybe billions of tokens, exploring every possible subquery, reading every paper ever published on the topic, validating every single step with a new retrieval.
The effective context length would be astronomical.
And if that scaling law holds, the accuracy might be genuinely superhuman. We might not need a bigger brain. We might just need the patience to let the current brains think for a really, really long time.
That is a fascinating, and I have to say a slightly terrifying thought. We're so used to AI being instant. Maybe the future of truly powerful AI is slow.
Slow, deliberate, and incredibly deep.
Well, on that note, we are going to leave you to process your own effective context length for the day. Think about your own inference budgets when you're solving problems. Are you guessing or are you iterating?
Always be iterating.
Thanks for listening to The Deep Dive. We'll catch you on the next one.